Okay, well, if we plug this in for M, I claim that the both of these terms are going to have an L and an ACS, right? And we got an ACS and an L here. That's going to go away, right? So we're going to get P2 minus P1. Boy, that one certainly started turning into 2, didn't it? Okay, P2 minus P1 is going to equal what you have over here if you plug this in and don't have the LACS, which means there's just going to be a row here, right? So this implies then that your change in kinetic energy pressure does not have units of energy. What's wrong?
Pressure's new.
Shouldn't there be a row underneath the pressure? Because there's not a row.
Well, there's no row in this term.
But there is.
Right, but there is in the denominator in the mass. Well, the way I do it.
There's no denominator here.
Well, yeah.
There's no mass on this side.
Well, you
Okay.
have.
You know, if I write this out.
But if you move over the original kinetic.
Oh, okay. Never
If
mind.
you move over kinetic energy with the initial
There's a
velocity.
denominator here, you mean?
Yeah. Well, yeah. I was looking off mine and I already had it in denominator.
Okay, so that's, well, that's actually volume then, isn't it? What's L times ACS?
Oh yeah.
Cross-sectional area times the altitude.
Right.
Okay, it's the volume, so, okay. So and this is not equal, this implies that the kinetic energy change over V is equal to 1/2 rho VF squared minus 1/2 rho V naught squared, right?
Right. Oh, okay. I see what's happening. Okay.
Okay?
Yeah.
Not written particularly well. That was really kind of ignorant of me, but yeah, that's par for the course. So we have this, right?
Right.
Which means that, among other things, that delta P is 1/2 rho. Looks like a P. There's a spot on the board there. It's a little low. Okay, 1/2 rho times VF squared minus 1/2 rho V naught squared, right? So, I could write this as 1/2 rho times the change in V squared. And that's not the square of the change in V. That's a change in the square of V. Make sense? Because it's change in the square of V is not the same as the change in V squared. Okay? And hopefully you understand the algebra of that very well, because it's a common pitfall. Okay? And the other thing is that somehow then pressure must be somehow related to kinetic energy per unit of volume, or somehow to equal to energy per unit of volume. Well, that's a puzzle we'll talk about a little bit later, okay? Now, the other thing we want to do is understand where pressure arises as you go deeper into a fluid. So, here's a container. There's a thought experiment that I like about this, but I'm not going to lay that on you right now, although I think it might be a good way to approach it. I'm going to approach it a little differently, okay? So if you've got this container and you've got some fluid of density rho, and the depth is Y, and cross-sectional area ACS. Then how much pressure does there have to be at the bottom of this container? Well, pressure is force per unit area, right? What's the force on the bottom of the container?
Y times ACS times rho.
Yeah,
Times.
you said it right.
Times, would it be times gravity?
Times what?
Gravity.
Oh, yeah, you didn't say it right.
Yeah.
I said it wrong when I said you said it right,
Yeah.
and you gotta have gravity in there, okay? Very good. Okay, so,
Yeah.
force, not four. Rho G A C S Y, right?
Right.
And there's symmetry involved, and I'm not going to get into the details of a symmetry argument, but by symmetry and other concerns that are maybe a little subtle, but the pressure is the same all the way across the bottom. Okay? We'll just accept that for the now, because we don't have a lot of time to spend on fluids. We want to get to electromagnetism a little earlier than I usually do. So we're going to just hit the main ideas here. Okay, so bottom exerts this force, right? So what is the pressure?
On ACS.
At the bottom.
It's rho G Y.
Yeah. Okay? Formally, I can write it like this. And you see your cross-sectional area just divides out as it has every time we've used it. And you get this. Okay? Now we have all the elements we need for Bernoulli's equation, and you can relate to how each of these comes about. So I'm going to write out Bernoulli's equation, which I did last time, but it's 1/2 rho v squared plus rho gy plus p is constant. Now, why these things should add up to a constant is just energy conservation. There's kinetic energy, okay?
So who
There's
is
potential energy.
Bernoulli?
I'm sorry?
Who is Bernoulli?
He's dead.
Who is Bernoulli?
Which one? There's a whole bunch of them. There's this family
Who is
of
this?
Bernoullis.
Who is this Bernoulli?
It might be Jacob, I forget, I think we called him Jake. Okay, pretty long time ago. Okay, pushing 200 years ago, maybe over 200 years ago. And they were all really profoundly good mathematicians and physicists. Okay, there was Daddy Bernoulli, and then there was Jakey Bernoulli. Okay,
So it was a whole family?
I think it was Daniel Bernoulli.
So the whole family came up with like a bunch of different equations together, or?
Or was it just like one
I think-
smarter than
I think
everybody
he's-
else?
he's fancy.
No, I didn't know.
This is Bernoulli's equation.
Okay.
In differential equations, you will
Yeah.
study solutions of Bernoulli equations.
Uh-huh.
You did. You too will. And I'm not even sure the same two Bernoullis are behind those equations because I'm a little fuzzy on my history. There are too many of them. I'm going to have to look at, I'm going to have to look and separate out what each one did. Google Bernoulli.
All right.
Okay.
Google Voice. Samsung Voice.
Brothers, cousins, fathers, sons,
Yep.
girlfriends, I don't know. I don't know the details. Okay. But there's a lot of Bernoulli stuff in mathematics, and these guys over 200 years ago. So, anyhow, you can recognize kinetic energy, potential energy, and some other kind of energy, right? And it's energy per unit of volume. Okay? This is actually potential energy due to altitude. This is potential energy due to other forces. Okay? But altitude's involved. So I don't want to go into detail on all that. It's a little bit subtle. I'll leave it for you as a mystery to be solved because we're not going to have time to do that whole discussion. Okay? But there's the equation, and let's see how it might be used. So let's just say we have the situation I talked about earlier, a pipe that narrows. Okay, so the cross-sectional area here is going to be A1, that's here. And here the cross-sectional area is A2. And here the velocity of the fluid is V1. And let's just say that, the average altitude here is the same as the average altitude here. This pipe is horizontal, not vertical. Okay? Well, first of all, you're going to have a V2 here, right? So in terms of the other three quantities, what is V2?